All right, moving on now, we're going to talk about infrared spectroscopy. Um, so IR spectroscopy relies on the fact that bonds are essentially vibrating. You can imagine that the bond is a spring. Between two masses. Okay, so imagine we have a spring between two masses. Well, you can stretch that spring, or you can compress that spring, right? Um, and if you do that, let's say you start by stretching it, it's going to start vibrating back and forth. Um, and essentially, that's the way bonds behave. Um, so we're going to use nu for frequency. Um, light also has a frequency. And it turns out that if the frequency of a photon of light equals the frequency of bond vibration, then the photon gets absorbed. All right. If not, then a photon will just pass right by the molecule. Uh, and it turns out that infrared radiation, so IR, um, has the range of frequency that roughly corresponds to the frequency of bond vibration. So it's IR radiation that tends to get absorbed this way. Um, Notice when that IR radiation gets absorbed, that's going to make the bond vibrate faster than it was, and then that's also going to end up transferring to the heat. This is why you have infrared lamps for food at cafeterias and such to keep the food warm, because the food absorbs the infrared light and warms up. So uh, typically the way this works is we have a light source. We pass it through our sample, and then it goes to a detector. Some of it gets absorbed, some of it doesn't. And we produce a graph that looks this way. Now, this graph, the way we talk about it is a little upside down, because the sort of valleys in this graph, these are called peaks, even though they're pointing down. So you might know that in caves you have stalagmites that point up, and you have stalactites that point down from the ceiling. These peaks are essentially the stalactites. Um, these represent the frequencies that are getting absorbed. Okay, um, so those give us interesting information. Um, you might notice the x-axis here is kind of labeled weirdly. It's frequency, but in per centimeter. Um, we have a name for this unit. We call this unit wave numbers. And you might ask, why are we using this unit? I think when this technique was developed, people were looking for, well, what's a convenient unit that's going to give us numbers that sound good to the human brain? And if you use the frequency, in terms of per second, um, those frequencies end up being really big numbers, and no one wants their x-axis to be in scientific notation. Um, so they said, well, what if we changed it to the frequency, how many waves there are per centimeter? And that gave us a scale here where, oh, look, it goes from about 500 to 4,000. Those are numbers that our brains are happier to deal with. So really, it's a unit of convenience, these wave numbers. Uh, One weird thing to note is that we usually put the slower end on the right. Um, so slower vibrations over here and faster vibrations over here. So it looks like our x-axis is backwards. Um, Again, someone's arbitrary choice and it's stuck. So this is the way these spectra typically look. Um, all right. So how are these peaks? How are these peaks intelligible to us? What do they tell us? Well, I'm gonna show you a little physics equation here, um, and that little physics equation essentially is related to Hooke's law for springs, um, and this is the frequency. So the frequency is going to depend on a few things. Well, first of all, we can ignore this because it's constant. So that part we're basically going to ignore. And then the other parts of this equation, you have this value of K. This is essentially a measure of the bond strength. In Hooke's law, this would be a measure of the spring constant for that spring. So a really stiff spring would be a strong spring, so that would have a high K value. And then a really loose spring would have a low K value. And then the M, these M values are essentially the masses of the two nuclei. Uh, so the thing I want you to take away from this, so because in the denominator you have M1 times M2, right? You're multiplying the two masses together. That's generally going to be a bigger value than M1 plus M2. So when you have bigger masses, that denominator gets really large. That's going to lead to slower vibration. All right. Think about this in terms of common sense. If you had a spring connecting two bowling balls, you would expect them to move much more slowly than if you had a spring connected to two tennis balls. Um, so bigger mass, slower vibration. Um, the second piece is K, and if you have a stronger bond, that's in the numerator, that's going to lead to faster vibration. And again, you can think of this in terms of a spring, like a stiffer spring is going to make things vibrate faster than a looser spring. So essentially, the frequency of the vibration um, and the and therefore the frequency of light that gets absorbed is going to be a function of how heavy are the two atoms in the bond and how strong is that bond. Great. So this picture here should be intelligible in terms of each peak representing a kind of bond based on how strong it is and how heavy the two atoms are that make it up. There is one extra rule, and that's I said a photon will get absorbed if uh, the frequency of the photon equals the frequency of the bond vibration. There is one more selection rule, and that is that vibration has to cause a change in the um, dipole moment of the molecule. So if you have a symmetric molecule like this one, and let's say I stretch that bond, I haven't changed uh, the the dipole moment of the molecule. There's no change in polarity if I do that. Um, if it's asymmetric, though, there is a change in polarity. When I stretch that bond, even if it's slight. Um, so only bonds that are not perfectly symmetric on both sides will actually show up. So for instance, this triple bond in this first molecule, this will not show up in IR. This bottom one will absorb. It doesn't come up that much, but you may see examples of this and just want to point them out. All right, so let's get to know the infrared spectrum. Okay, so first of all, we're going to break it up into 4 main regions. We've got like the way left end, so like 4,000 to about 2,800. This is where bonds to hydrogen are going to show up. So OH, NH, CH. These are very fast vibrating bonds. All right. You might ask, well, why are those very fast vibrating bonds? Well, think about it. Hydrogen has a very small mass, right? Hydrogen's mass is 1 compared to, carbon, which is 12. So much, much lighter. Having that very light atom leads to uh, a very fast vibration. Um, so bigger mass is slower vibration, small mass, faster vibration. Um, and then there's going to be a region in the like 2,300 to 2,100. That's going to be where triple bonds show up. So these are heavier atoms, but triple bonds are very strong. Right? And stronger bonds, we said, will have faster vibration. So of our bonds between heavy atoms, triple bonds will have the highest frequency. In the region between about 1,800 to about 1,500, that's where we're going to see double bonds. Mostly CC and CO, double bonds. And then in the region further to the right, this is where single bonds show up. Now, I am not going to bother getting into that region. It's very complicated. There are lots of chemists who can get a lot of information out of it. It's often very complicated. It's often called the fingerprint region. Because it's got complicated patterns. And usually, if you get a perfect match between a known sample's IR spectrum and a new sample's IR spectrum, you can say, okay, this is a perfect match. This is what that chemical is. We're not going to focus on this. You may, in a future organic chemistry class, be told to try and glean some information out of it, but I'm not going to tell you to do that. Just focusing in a bit on that bonds to hydrogen part of the spectrum. In that part of the spectrum, again, 4,000 to about 20. I said 2,800, maybe closer to like 2,600. That's going to have some peaks that are worth pointing out. So first of all, way over on the left, if you see a broad peak, let's say above 3,300, you see a broad peak over here, that usually represents OH. Now, occasionally, if it's a carboxylic acid OH peak, then sometimes it's even broader and even vaguer. Um, so a carboxylic acid OH peak um, can be even broader, and it'll often overlap with your other peaks. Uh, but a big broad peak over there is usually a sign of um, an OH group. Right around 3,300 is usually where you'll see NH peaks. If it's an NH2 group, you might see a double peak. If it's only one NH bond, then you'll only see one peak there. And then around 3,100 is usually a dividing line. To the left of that, you might see peaks that look like this, a little bit sharper than those OH peaks. These could be SP hybridized carbon-hydrogen peaks. Just to the right of that, in like the 3,000 to 3,100, you could have your SP2 carbon-hydrogen peaks. And to the right of that, you'll have your SP3 hydrogen peaks. SP3 carbon-hydrogen peaks. I don't usually focus on these much. The reason being that pretty much every molecule has carbon-hydrogen bonds. So these don't offer us a ton of diagnostic information. But you will see in most spectra, for example, you take a look at all the spectra, they all tend to have some peaks around 3,000, a little below 3,000. Those are representing carbon and hydrogen. So in pretty much all of these, there's carbon, hydrogen. So that's why I say I wouldn't focus on them so much. One last thing, right around 2,700, a lot of times you see kind of a sharp fang. These are often called aldehyde fangs. So that can be an indication that you have an aldehyde group. You don't see them that often, but when you do, it's kind of a giveaway. All right, so let's look at some spectra and talk about what I want you to see. And really, the four things I want you to look for would be carbon-carbon double bonds, carbon-oxygen double bonds, and then triple bonds and OH bonds or NH bonds. All right, so this first one is an alkane, and it's pretty boring, right? You've got your CH peaks over here, pretty boring, and then nothing until you get to below 1,500, right? So I'm usually cutting myself off there, and I'm not looking over here. But this is a boring molecule. The IR doesn't tell us much. When I have an alkene, what's different? Well, now I do have above 3,000. I have an sp2 hybridized CH peak. All right, that that's one clue that this is an alkene. The other clue is my peak right at about 1600. CC double bond will usually be right around 1600. Um, so when I see that, that tells me it's an alkene. Okay, an alkyne, that's got a CC triple bond, and you can see the triple bond peak right here. This one's at about 2100. This one also has an SP hybridized CH peak. Over here on the left. Um, like I said, I'm less focused on those CH peaks, but sometimes they can be helpful. All right, now an alcohol. Aha, here's all the way on the left. Here's my broad. Let me try and be consistent in terms of colors. I've used green and orange, so I'll use pink for my OH peak. Big, wide, usually a good indication that you have an alcohol. And then ketone is going to have another very common peak that I want you to be able to identify every time. And that is right around 1700. It's your carbonyl peak. So your carbon double bonded to oxygen. So 1600 carbon double bond, 1700 carbon oxygen double bond. And a carboxylic acid, I also see that CO peak. And this is where I have the OH that got swallowed up. This is my carboxylic acid OH that's just really broad and overlapping. That's a sign that I have a carboxylic acid in my molecule. All right. This next molecule is an aromatic ring. You will notice it does have the 1600 peak for carbon-carbon double bond. There's often also these peaks here that are called overtones of the benzene ring. They're not always there, but if you see them along with a CC peak, it's usually a good indication that you might have an aromatic ring in your molecule. You can see the same thing in the next molecule. Here you've got those overtones, but you also have your CC double bond peak at 1600, and at 1700 you've got your CO double bond peak. And one more thing you've got is those aldehyde fangs. So, you know, the carbon double bond to oxygen along with the aldehyde fangs tells me it's an aldehyde, and the carbon-carbon double bond with the overtones, that tells me that it's a benzene ring. For a nitrile, I would expect a peak in the triple bond range, which I have here. That's representing my CN triple bond. This one's at about 2200. A couple more examples of molecules. Here I've got another carbonyl. Here I've got an amine, so it's got that NH2 peak with the two bumps. And then an example with an amide. The amide is going to have the carbonyl peak. It's going to have the C double bond to C peak. It's well in this case because of the benzene ring and the overtones. And then notice this one has an NH peak all the way over on the left because of the NH bond here. All right, so those are some examples. And if you're looking and saying, how the heck am I supposed to pick this out? You do it by practice. So you're going to see a lot of examples. And in those examples, you'll start to get a feel for recognizing these peaks and the way they tend to show up. So if this all seems like just madness to you, give yourself a little time to digest and then dive into those practice problems. And there, once you've seen enough examples, things will become a lot clearer.